Thank you, Andrew. Good morning, everybody. Good morning, good afternoon to those of you who are online. So, as Andrew said, my name is Eric Mackay from Heriot-Watt University, and I hold the Energy Simulation Chair in CCUS and Reactive Flow Simulation, along with my colleague Arne Skauge, who unfortunately isn't able to come to this meeting for family health reasons. So I'm going to be talking a little bit about the impact of CO2 storage in tilted aquifers, particularly, as a topic that's starting to become of primary concern both in the UK waters and in the Gulf of Mexico. So a few weeks ago, I was asked what my main contribution in my work was. And my answer was, I think, possibly slightly unexpected to the question. And I said, it's training people to work in the industry. Now, we've seen that we're going to have to ramp up CCS, and that means lots of things. It means finance primarily, perhaps, but it also means people working in the industry. I don't think you're going to open a GEM manual page, CMG GEM manual page in 10 years' time and find the Mackay equation for CCS in there. I don't think you're going to find 5 Nature papers on scale in production wells. But I hope that you will find people who are motivated and energized and somewhat equipped to work in the industry as part of the energy transition. And I hope I will have had some contribution, perhaps some positive contribution towards that at some point. So there's a bunch of students you can see on here. Actually, can I ask you to make this a pointer on the screen, if you would, please? If you go up to pointer options, yeah, thank you very much. So the ones I've put in the green with a dotted line are students who haven't yet, who will be graduating within the next year. They're already working for organizations and they have jobs to go back to. The ones in the solid green are just finishing off, and they have been offered new jobs working related to CCS. And I'd like to introduce to you Tosin here, who's here sitting at the table over there, Tosin, and Mattia, who are both students who will be finishing within the next year and will be open to positions. So my job is to try and sell their work. So what I'm going to do during this time is give you some highlights from their work and one other student that have been carried out. So the chair is working on looking at fluid-fluid and fluid-rock interactions in the subsurface where chemistry might have some impact. And so we're using reactive transport modeling to model CCUS and to some extent hydrogen storage in the subsurface, I should say CCUS. So part of these projects are looking at CO2 enhanced oil recovery as well. We're looking at mineral scaling in production wells, and part of that is, most of that is trying to prevent mineral scaling. We have one somewhat failed researcher who's trying to create mineral scaling for plugging in abandonment scenarios. I'll mention that briefly in a moment or two. And then we're also looking at chemistry in enhanced oil recovery processes such as CO2 WAG, or where the injected water composition is being altered to achieve some effect. And so the problems that we're trying to deal with are primarily CO2 and hydrogen storage, and the efficiency of whatever remaining oil and gas production we will have. So every month I get an email from an organization called the North Sea Transition Authority. And this is a standard email. It's not a personal email from them. It's a standard issue email. It just lists the activity that's taking place in the North Sea, in the UK waters of the North Sea over the past month. In green, we have development of wind farms. So we can see in October, they announced some activity in one wind farm. The purpley ones are to do with ongoing oil and gas production. And the UK government has, the current administration have indicated they will be issuing no new licenses in the North Sea at all. So we expect that purple bit to be declining somewhat over time, but it's not going to happen overnight for sure. The red ones are field abandonments or well abandonments and so on. And the blue ones, the light blue ones there, you can see two of them, are CCS projects. And we expect those to increase. Indeed, they are generally increasing. So what's our role? Well, our role is actually in all of the, well, apart from the wind farms, and trying to keep the wind farms away from the CCS projects because they affect our ability to monitor them. But apart from that, our role is in all of these. So what we're trying to do, and the big thing we're trying to do across all of these, is try and reduce cost and try and reduce and manage risk with all of these activities. So that means optimizing oil and gas production, and actually in the case of the North Sea, actually predominantly means optimizing, trying to manage water production. We produce far more water than we do oil or gas in the North Sea, as it's a mature basin. And that means trying to reduce the amount of mineral scaling that takes place, and also minimize the carbon footprint. So a barrel of oil produced at a 99% water cut, which happens quite routinely in the North Sea, has a much higher CO2 footprint than the barrel of oil being produced at 10% water cut because of all the extra water handling. So trying to address that. And Arne's chair in particular is looking at that issue. I mentioned that we're looking at, so we've spent decades trying to prevent mineral scaling in wells, and one of our researchers has developed a new technology called Rocket, which is looking at deliberately precipitating scale in the near wellbore region to the parts that cement cannot reach in order to provide a barrier that isolates the formation from the wellbore. Not acting in competition with cement, but in situations where cement is not able to function to the full effect, either in support of cement or where cement may be damaged. And it's a solids-free and low viscosity system, so it's quite pumpable, and it provides sealing at the pore scale level and provides a permanent barrier which is insensitive to acid gases, for example, as well as temperature and pressure. And I'd say, so Brian, who's here and is going to be speaking at lunchtime, sorry, I've lost you in the audience, Brian, has been very helpful, as have other people here in Calgary in the past couple of weeks, in terms of looking for opportunities, particularly amongst orphaned and abandoned wells here, for which there's a large demand for being able to seal them off. So that's an interesting activity, and please feel free to come and speak to me about that afterwards if you're at all interested. But the main activity is looking at the developing CCS industry. Now, Hadi had a figure from his paper with Sam Crever identifying somewhere around 30 megatons. It depends on of CO2 storage taking place today. It depends on how you exactly define, because there's a lot of CO2 being used for enhanced oil recovery, and the drivers for that can vary from location to location. So another metric of that is around 50 megatons on 40 projects worldwide. And Brazil are leading the world in terms of their ability to inject CO2 and develop the knowledge. And if you hear anyone saying that CCS is an unproven technology, they're talking complete rubbish. It's been done since CO2 injection has been done since the 1970s. There are issues, of course, and a lot of work still needs to be done, but we're perfectly capable of injecting CO2 into the subsurface. It's the economics and the management of risk that are the challenges that are facing us just now. And I think Andrew identified various scenarios in his plots, and so the requirement is something of the order of 3 gigatons of CO2 injection by 2040 to be taking place on an annual basis. So that 3 gigaton figure there is in order to meet the temperature change targets that we currently have. And the figures that Andrew was showing were for the current projections are somewhere around here. So there's still quite a bit of work to build up to get to that point. In the UK, the first targets are liable to be depleted gas fields that Hadi was talking about, with all the associated challenges of phase change and Joule-Thomson and effects and hydrates and freezing of fluids in the subsurface. I suspect we will move quite quickly on from those to look at storage in saline aquifers. And indeed, the next bunch of licenses that are coming up have tended to be for storage in aquifers, not in depleted gas fields. I also think we'll pay a lot of attention to depleted oil fields. I think there's a lot of potential in depleted oil fields coming up. Anyway, what we're doing in our research chair is basically using reservoir simulation as a tool that helps us to learn. We can look at real-life scenarios, we can devise synthetic models to address specific issues, and identify interferences that may take between CCS projects and other users of the subsurface, because we're tending to deal with mature hydrocarbon basins where there's a lot else going on as well. And so we need to understand how those interactions may take place, both in the subsurface and actually if there are surface users of potable aquifers, we need to be careful about our interaction with them. And trying to identify whatever opportunities there may be synergistic opportunities, there may be risks associated with these projects in the same locality. And so I'm going to show you 3 examples based on the work of 3 students at basin, field, and near well cases. So the first one is Matthias' work. You can, if you can read his poster, you've got far better eyesight than I have on the right there. But go and speak to Matthias at his poster and have a good look at the detail in there. What Matthias is looking at is the Bunter Formation in the North Sea. So the UK's first project, CCS project, will probably be the Northern Endurance Partnership project in licence CS001, imaginatively named. But that is a wider system which is connected to quite a few other potential storage sites and 1 or 2 depleted gas fields as well. So there will be interferences there. And we're not just seeing that in the UK, so the Miocene in the Gulf of Mexico is another area that's been identified as having a lot of potential, and it's a dipping structure. Some of it actually does outcrop, I believe, on shore in Texas and Louisiana. And Alex Bump and Susan Havorka at Austin have identified that actually pressure management for these systems is going to be quite a significant factor. So the methodology that Matthias has been looking at is, say, injecting something of the order of 14 megatons per year over a 50-year period, and looking at that in 6 license areas and trying to calculate both the CO2 migration pathway, so making sure that the CO2 remains within the license areas, and also what is the impact on pressure and how far does the pressure field propagate. And obviously the pressure propagates much farther than the molecules of CO2 themselves do. And so looking at trying to understand the impact of flow, particularly at the boundaries of the system, and understanding what impact that has on the pressure responses within the system. And one particular boundary of the system is a known subcrop near one of the existing, the Endurance project, and BP have actually drilled a well into that subcrop and identified that there's potential that's open to flow. So there may be a pressure release mechanism here that's going to take place. And then Matthias run these models for 5,000 years after the 50 years of injection. So there's the Bunter. So the area of interest that he's looking at is that little blue bit there. So that's that area there. He's gathered a huge amount of data from a whole bunch of sources in order to build his model, and looked at these various scenarios for CO2 injection. And then he's run the models, and on the left we're looking at the CO2 saturation distribution within the system, and you'll observe that as the CO2 injection is taking place, and then for the 5,000 years afterwards, all the CO2 just about stays within the license areas, which would obviously be a requirement. Now, had he identified that grid resolution is a problem in these types of calculations, we're working at a much larger scale in an individual field, and these results would have to be verified with higher resolution in the local areas. The chances are that the CO2, the calculations actually show that it migrate a little bit further. But the main point of interest, and I'll rerun the simulation again, if you look at the one on the right, that's the pressure response in the system. And you can see the location of the outcrop, which is just there. And the pressure doesn't change at that point there over the duration of the simulation. It's assumed to be an open boundary, open to the seabed. And so we're tracking the CO2 plume as it moves through the system. We're also tracking, Mattia is also tracking the pressure changes that are taking place. And so if we take a cross-section through the system, say a straight line across the bottom here, there's the Endurance project. Assume a couple of injection wells there. There's a subcrop to the seabed and extending on for about 80 kilometers. And I should say the system, so order of magnitude, we're looking at something that's of the order of magnitude of 100 kilometers by 100 kilometers, much bigger than typically we're doing our reservoir simulation calculations for in an oil field scenario. So to Dennis's point, that's a significant difference that exists between these types of modeling activity and creates the challenges. So if we assume that the subcrop is maintained at a constant pressure through its contact with the seabed, what we have in the solid lines, every line represents a decade, so there's 5 decades of injection and an increase in pressure. The dotted lines are given are 10, 20, 100, 500, 1,000, and 5,000 years. And you can see that for the first period here, up until about 500 years, there continues to be a pressure increase in some parts of the system. That's a period after stopping CO2 injection. The CO2 pressure impact is continuing to increase at some distance away from the injection points. At the injection points, the pressure is actually decreasing. But so the point here is that we're seeing pressure impacts at long distances and changes over long periods of time. And so this plot here is showing the amount of water that will be expelled from the system through the boundaries, including that subcrop to seabed, over the 5,000-year period. And we note with interest that the highest water expulsion rate, which is about 3,400 standard cubic meters, or for those that you work in barrels, that's somewhere between 20 and 25,000 barrels a day. So a good going production well in an offshore environment. That flow it reaches its highest value some period after, 14 years after stopping the CO2 injection. So the pressure effect is being felt over a long period. And in fact, water is still being expelled from the system 5,000 years later. So, okay, we're down to about 1% of the flow rate, but there's still a sizable amount of water being expelled after such a long period. And I should say also that that volume, that total volume of water, just shy of about 1 billion cubic meters of water being expelled, is only about 3.5% of the downhole volume of CO2 that was injected in this system. So that means that 96.5% of the volume occupied by the CO2 when it's injected is being taken up by compressibility effects and by dissolution of CO2 into the water. Actually, a relatively small fraction of the fluid volume is actually being expelled from the system. So that's Mattia's work. I'd encourage you to go and speak to him at his poster if you're interested in learning more about that. The second is a student who actually graduated last year, Mauda. She's relocated to Calgary for family reasons and is open to employment opportunities. So I'm highlighting her work. I've mentioned to you before her study on CO2 injection in a tilted aquifer. So this is more the reservoir scale rather than the basin scale. And looking at 2 years of CO2 injection and 30 years of shut-in, and looking at the plume migration. And the key control, after cessation of injection, the key control on plume migration is the difference in height between the highest point and the lowest point in the plume, because that's what's giving the buoyancy force. That's the main factor. And so that was a system tilted at 2 degrees, a system tilted at 10 degrees, for example. As you'd expect, the plume migrates much further and thins out. The reason it's migrating further is that the buoyancy force is greater. The height there is greater, and so it's traveling faster and further. However, there are advantages in this. So here we have a plot of what's defined as the CO2 inventory. So we have, if we assume a certain, if we make this dimensionless, we assume that we've injected 1 unit of CO2 into the system, whatever that is, a gigaton or whatever it might be, then at the 2-degree dip angle, after 30 years after cessation of injection, somewhere a little bit over half of the CO2 is trapped as a residual phase. If we increase that to 10 degrees, then we're up about 80% of the CO2 is trapped as a residual phase. The consequence of that is that there's much less CO2. So this is the mobile CO2 at 2 degrees, still about 40% of the CO2 is mobile after 30 years, but at the 10 degrees, it's down about 10%. So, okay, the CO2 plume is migrating further, but there's less mobile that could leak out if there was a leakage pathway for it to leak out. So there are pros and cons to these dip angles. However, the main finding of our work was that because of the plume migration, as Hadi said, this happens, these processes start to occur the minute you inject CO2 into the system. The CO2 plume during the injection period is migrating quite fast away from the wellbore, but then decelerates when you stop injection because the bottom of the plume is rising up towards the cap rock, and so that H is getting smaller, and so you get a rapid deceleration. But once the plume is starting to migrate away, that rate of deceleration levels off, and at the 10-degree dip angle, it might actually start to accelerate again, because the plume is stretching, which means that the H is getting bigger, and so it's moving faster. She also looked at if there was groundwater flow in the vicinity, looking, for example, here at injecting, having a water injection well to simulate an active aquifer flowing at just 0.1 feet per day through the system, and we can see those rather attractive plumes of CO2, so convective currents, with CO2 dissolving in water, the water becoming denser and falling down and going towards the bottom. And then because of the 10-degree dip angle, that denser water, which is saturated in CO2, actually still migrating down dip. Increase that groundwater flow to 0.15 feet per day, so by a factor of 15, and we start to disrupt these density-driven fingers that we see. The process becomes much more uniform, and more significantly, that plume will now start to migrate up dip. So only 0.15 feet per day background drift flux is enough to be driving that. Now, if we're concerned about CO2 being trapped in the reservoir, then we need to keep an eye on where the brine that's saturated with CO2 is moving to. And the final thing that she identified was that if we've got up-dip brine flow, we'll get a plume occupying a certain range. If we've got down-dip brine flow under identically the same conditions, the plume will actually travel much further for this 10-degree dip angle system. And that's again because the downward flow of water is tending to stretch out the plume, increase the H, and it's migrating further. Okay, and finally, I want to move on to the second poster, which is here, which is Tosin's one, looking at halite precipitation. So this is a near-well radial modeling activity. And the main learning from Tosin's work is that if you're injecting at a high rate, you will be displacing CO2 throughout the entire column of the well into the formation, and eventually gravity will start to take over, but in the near wellbore region, it'll be viscous dominated, and the dry out zone, which is shown in red here, if you're injecting at a high enough rate, in the near wellbore zone, will have a vertical front moving into the system. However, as we happen to decrease the injection rate, then we will notice that gravity is starting to have more an effect closer to the well, and there's a feedback effect in here in that the CO2 that is being injected is more, as Hadi said, is more mobile, and it's more mobile than the water that's being displaced. And so subsequently injected CO2 will find it easier to go into the top of the system, and we'll get water flowing back in towards the bottom of the well. And it's this zone here where there's mobile brine in contact with the dry out zone. Under capillary pressure, that water will be invading into the dry out zone, and that may then lead to precipitation of salt. And the blue here, this is a porosity loss effectively, and the blue here indicates complete loss of porosity at the bottom of the well. Does it matter? Well, actually, that part of the well wasn't injecting any CO2 anyway. So it may have some impact on the injectivity. But at the lower rate, as we see here, there's more of an effect of gravity, and so the plume is rising more to the top, and we're not actually using the bottom of the well. And there's more opportunity for that brine to come in contact with the dry out zone and cause a precipitation. And actually Tosin's identified that if the brine isn't completely saturated with salt, there may actually be a self-healing process, a cleaning process going on at the bottom of the well, whereby already deposited salt is starting to be dissolved back out again. Okay, so in conclusion, at basin scale, we're identifying that obviously we'll want to keep the CO2 plume away from abandoned wells and other potential leakage sites, but nonetheless, actually large dipping aquifers might represent an excellent storage opportunity because of their very large volumes. And it's just a matter of managing the plume and where it migrates to, but it's probably also going to be a matter of looking at the pressure response of the system. But we may need to consider brine expulsion from the entire system over periods of centuries and possibly even millennia. Now, offshore, that was a subcrop to the seabed. That's not too big a concern, probably. There's some concerns around that, but it's putting salty water into the sea. If that system were outcropping onshore, then that would be a different matter. There'd be a much greater concern about the potential for damaging freshwater usage in the shallow formations. And so a lot of attention would be required to be paid to that. At the field scale, we need to think about the physics of the processes that are going on and what forces are taking place. And as reservoir engineers, we tend to spend a lot of time thinking about the impact of viscous forces. With CCS, especially after cessation of injection and following on for maybe taking place over decades and centuries, we need to consider much more in terms of gravity and capillary forces. And the plume will actually accelerate during the initial period of injection. When injection stops, the plume will decelerate. But as the plume rises to the top of the bottom of the plume rises to the top of the reservoir, it may then accelerate again if it's a steeply dipping system. And so we need to be able to keep track of where the plume is going, particularly complicated if there is groundwater flow in the system. And then finally, at the near wellbore scale, we should be thinking about the length of our completed intervals and making that appropriate for the injection rate that's going to be used. Now, as Hadi mentioned, in the depleted gas fields, the strategy is perhaps to inject at a lower rate to begin with until the system is lifted above the critical pressure, and then to increase the rate. So what does that mean for the length of the completion? Would we be looking for a longer completion or a dual completion? Because we want to avoid injecting at a low rate where we might have these salting out processes taking place at the bottom of the CO2 column, as it were. And with that, I'd like to acknowledge and thank our academic partners for their support, and also Energi Simulation for their support, and Computer Modeling Group for making software available to us, and the various industrial sponsors of our research projects. And thank you for your time.
Thank you, Dr. Mackay. Instead of cutting into a student poster session, which equally as important, I'll just ask one question online, which is quite a good question that I would have myself as well from Dr. Kaveh Dagani, former Chevron. With all these simulation runs, modeling efforts and whatnot, looking at plume sizes and pressure, his general dilemma is how would you validate your results with long-term forecasts, like 5,000 years or 100 years? How would you validate that? Even
it's a good question. I'm not planning around and being around in 5,000 years' time to take the blame for any calculations that go wrong. So it's a very relevant question. Any operator will want to hand over their system to the competent authority, the regulator, at some point in time. In order to be able to do that, they will need to be able to demonstrate that their simulation model conforms with observed data to date, however long that may be. And there's quite a lot of discussion going on about whether that, should be a matter of a decade, a couple of decades, or whatever before handing on. Obviously, companies will not be able to extend for very long periods. So the ability to validate the model, even while the plume is still migrating, until such a point as it's handed over to the competent authority, will be the key question. So what are the monitoring techniques that need to be used for that?
Okay. So for Dr. Rick Chalatrinic, I offer him one more question.
Thank you, Andrew. Very appreciated. You mentioned Alex and a bunch of people. There's lots of stuff happening in Alberta around pressure movement. And almost exclusively, there might be a lot of people in this room who can correct me if I'm wrong, almost exclusively, the modeling is done with an impermeable upper boundary and an impermeable lower boundary. And so some pretty striking, probably worrisome comments are being made about large-scale pressure movement. And I'm a little worried that, in fact, those are actually incredibly wrong. So I wonder if you might comment on, we have these hydrological categories of aquifers, aquitards, and aquicludes. And so you've automatically assumed, not unlike everybody else who does it, that they're aquicludes, but at that scale, they're not aquicludes. They're going to serve as aquitards. And there's going to be a huge amount of energy dissipation that happens at scale. So could you just speak to that about how should we be doing this?
So it's a matter of volume and of surface area contact. So to that point, we have run some simulations where we've said the underburden rock is not actually completely sealing, but has a very modest permeability, 0.01 millidarcies. So very low, and you think, well, that's really not going to have much of an impact. Permeability is essentially in dimensions of area. These interfaces are over huge areas. So that 0.01 millidarcy actually integrates over a very large area to be have a significant impact on pressure dissipation. So if you've got enough volume beneath that interface, even a very modest permeability will effectively soak up a considerable amount of pressure. And so these simulations are indeed, the ones that are just using completely closed boundaries are indeed way overestimating the amount of pressure response that there will be in the system. I think there may also be stranded hydrocarbons in these systems that will also help absorb some of the pressure, so some of that pressure may be released again over a longer period of time. There'll also be surface uplift and such processes that will do it. So we are kind of looking at the extreme worst case examples. But to your point, Rick, I think it is appropriate that we look at pressure migration through the cap rock and through the underburden rock as well as an integral part of these calculations, just to make it even more complicated than it is already.
Okay, so once again, thank you, Dr. Mackay.